Today, we're going to tear into a paper that basically challenges a 40-year-old habit in economic modeling. Now, the title is a mouthful, Joint Bayesian Inference about Impulse Responses in VAR Models. But what it's really about is how we predict the ripples, the chain reactions, after a big economic event.
So let's kick things off with a huge question you hear all the time. When the Fed raises interest rates to fight inflation, what actually happens next? I mean, yeah, we expect a slowdown, but how much of one? And when does it hit? Does production dip right away, or does it take a while for inflation to cool off? How do all these moving pieces dance together over the next, say, year or two? Getting these answers right is a really big deal.
To get a handle on this, economists have this go-to tool called an impulse response function, or IRF. The best way to think about it is like a flight path for the economy. You introduce a shock, like that interest rate hike, and the IRF tries to chart the trajectory of GDP, inflation, unemployment, you name it, over the next few quarters. It's our best shot at seeing the ripple effect from a single decision. But, and this is the whole point of this paper, there's a twist. It turns out the standard way of drawing these flight paths for decades had this hidden and honestly kind of bizarre flaw. Let's call it the Frankenstein graph problem. Okay, so here's how the old way worked. Economists would look at each moment in time, one by one. They'd figure out the most likely outcome for month 1, then they'd do a totally separate calculation for month 2, then another for month 3, and so on. And at the end, they'd just connect the dots. The paper points out this is a lot like building a person from spare parts. You take the average height from one group of people, the average arm length from another, and the average leg length from a third. Sure, you get a result, but the final creation could have proportions that are just physically impossible. And this is what you get. That jagged red line there is the result of that old connect-to-the-dots method. And here's the crazy part. It shows an economic path that is totally impossible. The very model that was used to create it says this specific up-and-down journey could never happen in the real world. It's a statistical Frankenstein, a jumble of parts stitched together to create a monster that just shouldn't exist. And look, this isn't just a fun little analogy. It's a serious statistical flaw. The authors say it directly in the paper. And I'm quoting here. The old methods may imply impulse response function shapes that differ from the shape of the response function under any possible parameterization of the underlying model. Okay, let's put that in plain English. It means the picture they were showing us was a complete fantasy, a path the economy could never actually take according to their own rules. So if connecting the dots one by one is the wrong way to do it, what's the right way? Well, the paper's solution is actually a really beautiful and simple idea. You have to look at the whole picture all at once. It's called joint inference. So instead of asking, what's the most likely outcome in month 1, and then again for month 2, the new method asks a much better question. What is the most likely entire path, the most likely complete shape from the very beginning to the very end? It treats the whole flight path as one single thing, not a bunch of disconnected dots on a map. So how's it work? Well, it's this really elegant 3-step process. First, the model generates thousands of possible, complete flight paths. And each one of these is a totally valid, internally consistent story of how the economy could respond. Then it sifts through all those thousands of plausible stories to find the one single path that, as a whole, is the best fit for the data. And the result? You always get a believable economic story. No more Frankenstein monsters. But fixing the Frankenstein problem was only half the story. The paper uncovered another equally massive issue with the old method. It gave us a totally false sense of certainty about the future. You know how when economists make a forecast, they don't just give you one line? They show you error bands, that shaded area that's supposed to show the range of likely outcomes. Well, the paper found that the old point-by-point method was making those error bands way too narrow all the time. It's like a meteorologist telling you a hurricane will land in a tiny 10-mile cone when the real zone of uncertainty is actually 30 miles wide. The predictions just looked way more precise than they ever really were. The new method, on the other hand, gives us a much more honest picture. Instead of that one clean line with those neat, tight bands, we get this, a shotgun plot. Each one of those red lines is a plausible path the economy could take. Now, it looks messy, I know, but here's what's so important. That messiness, that wide spray of possibilities, that's honesty. It's a truthful picture of just how uncertain we are, showing us the full range of what the model thinks could happen. So, just how much were we understating the uncertainty? Well, in some cases, the paper finds that the true range of possibilities, the width of that shotgun blast, is up to 3 times wider than what the old error bands were telling us. That's a huge difference, especially when you're making major policy decisions based on this stuff. Okay, so we've got a new method, it avoids these impossible outcomes, and it gives us a much more realistic view of uncertainty. But why does this really matter outside of, some academic journal? Let's talk about the real-world impact here. This really is a major upgrade. First, by getting rid of those Frankenstein graphs, it makes sure our models are actually connected to reality. Second, by giving us that honest sense of uncertainty, it helps policymakers make smarter, more robust decisions because they're aware of the real risks. And maybe the most important thing is that it helps economists ask way better questions, not just about what happens at one point in time, but about the entire shape, the timing, and the story of an economic event. When you step back, this paper does so much more than just fix some statistical quirk. It forces us to take a hard look at the tools we use to understand our world. And it leaves us with this really powerful, lingering question. If a standard method that we've used for 40 years was literally creating pictures of an economy that could never exist, what other fundamental assumptions in our models should we be questioning?